Everybody. We are going to go ahead and get started. Thank you all for being here today at HMSC's research seminar. My name is Cinnamon Moffett, and I am the research program manager at Oregon State University's Hatfield Marine Science Center. That sounds a little weird for those of you in the room, but we also have a large group of folks that are joining us online. So for those folks that are online, thank you so much for being here. We do have somebody who is helping you out. So if you're online and you have any questions, Roseanne will be able to help you. Just put those questions into the chat. We also have a bunch of students that are joining us for seminar for credit. So Michael Banks is their instructor. Michael, can you turn on your camera and introduce yourself?
Yeah, I think you can hear me. I just want to welcome you all. This is what I look like, and I just wanted to give you good wishes for the seminar program. I hope you enjoy it. And also just heads up, please be brief in what you write up for me. There are a lot of you, and you'll be dinged if you write more than half a page. Thank you.
Wonderful. And thank you everybody for being here. Couple of quick announcements. Again, if you are online, please use the chat to put in any of your questions at any time. And then at the very end, you are also welcome to raise your digital hand. We will be able to unmute you and you can ask your question that way. For folks in the room, if you are new to our seminars, please know that because we have folks online, you need a mic to ask your questions. So you can do that in two ways. You can either go to the mic stand, which is up here, or you can just raise your hand and I'll bring the mic to you and you can ask the question. And we'll get to those mostly at the end. But if you have a clarifying question, feel free to raise your hand and we'll hit you during the talk as well. Okay. A couple other just a little quick announcements. We are recording today's presentation, so if you want to share it with others, it'll be posted on the HMSC past seminar page in a couple of days. And then I wanted to promote a couple of talks that are coming up. Next week, we have Sean Rowe with Sea Grant and Susan Rowe with Pre-College Programming coming to talk to us about using virtual reality to increase ocean literacy. So completely different topic. It should be really interesting. And they have some of the headsets to share with us. So that should be kind of fun. So come next week. And then if you haven't heard about it yet, the following week on October 5th, we are doing a Science on Tap with the Big Fish Lab and Taylor Chapel. And we are going to talk about sharks. It's a good way to kick off October for that are here in Oregon. And then we're going to do a shark dissection here in this room. We're going to have overhead cameras pointing down at the shark, pointing up at the big screen. So everybody's going to have a great view of the dissection. So if you'd like to join us for that, you might come early. Just a heads up. Okay. If you're curious about any of our other events, they are on the HMSC homepage. You scroll to the bottom of events and you will see a calendar there that gives you all the details. For today, today's speaker was brought to us by our iLab manager here at Hatfield, Drummond Wingrove. So I'm going to hand this off to Drummond, and Drummond is going to introduce today's speaker.
Thanks, Cinnamon. So I was really happy that Bryson agreed to come here and give us a chat and kind of talk about PMEC. And so I want to give you a brief history just so you understand where he's coming from. So Dr. Bryson Robertson is the director of the Pacific Marine Energy Center at OSU. Nice, short and simple acronym. I appreciate that. And an associate professor in civil and construction engineering. His research focuses on wave mechanics, hydrodynamics of floating bodies and mooring systems, and renewable energy. Working with partners in industry and academia and the National Laboratory, he specializes in waves and offshore wind energy resource characteristics. The co-design and modeling of hydrodynamically active offshore wind and wave renewable technologies and numerically integrating marine power with the emerging blue economy. I'm not going to do that 10 times fast. In the complementary research, Dr. Robertson also looks to the future of our global energy systems and the nexus of technology, climate change, policy, economics, and the society on the decarbonization of electrical systems and the public trust requirements to transition to these power systems. So with that, I'll hand it over.
Apologies, I've actually never tried to say that bio, so that doesn't quite seem fair. And also in true sort of Canadian style, I'm going to start my presentation with apology. I got way too excited about some of the slides today to actually prep trying to say them from beginning to end. So my goal is here, hopefully we've got enough slides that are sort of interesting, spark a conversation. If we don't get to the end, I'm not too concerned about it. I'm going to try and keep somewhere on schedule, but really the goal here is just to spark imagination and try and understand where does marine energy fit. You'll notice the title doesn't match the title of the presentation. That's because I forgot to update that today. So that gives you a context of where I got excited about my slides and didn't get through everything. So we will get to, there we go. So I think what's important to start here is that the past does not represent the future. For a long time, I think we've been able to do that. We've been able to go through the slow progression where we look back at historical trends and things that have been done in the past and be like, that seemed to work. Let's do that. Let's not do that. But I think fundamentally right now, the past cannot represent the future. We cannot look backwards to understand where we need to go forwards. There's just been two fundamental changes. And the biggest one about that is the paradigm shift of climate change. Never before have we had all the knowledge to understand what we're doing to the planet, and we're slowly killing ourselves. So things that we do now, I'm of the opinion, and again, this is just my personal opinion, that we need to keep that perspective on the things we do. We know where we're going if we continue on this trajectory. And it's really a question of what are we going to do? What risks can we take? How aggressive are we going to be? Where are we going to make changes such that we can mitigate the worst impacts? So this was from the OCRI, the Oregon Climate Change Research Institute, which is also an OSU group, just for the Pacific Northwest. They're looking at temperature rise by 5 degrees by 2050, increased rainfall in the winter, reduced rainfall in the summer, increased forest fires. I think we've all seen that, increased flooding, increased ocean acidity. It's really not a very positive picture if we continue to use the past to represent our future. So understanding that climate change is primarily driven by emissions, you know, I'm an engineer, so the first thing I'm like, okay, well, tell me where the emissions come from. Where do I put my energy? So on the left-hand side, these two slopes, these are just some things I pulled off the EPA website yesterday, trying to look at where are our emissions, what do they look like? And 80% of our emissions are carbon dioxide that are affecting the climate change. Now, look, and there's a big discussion about which one has more impact versus volume, but let's say we're just working with carbon dioxide. The lower plot is how have our emissions across different sectors changed over time. So understanding that transportation and energy, or the electric power industry, have sort of dominated that picture for a long time. You know, if we look at the truck and the power line there, it's more than 50% of our emissions are coming from those two sectors. Let's start to focus on those. And you know, this picture, the graph at the bottom shows us sort of a good picture, like we're reducing that. And that's primarily driven from a shift from coal generation to natural gas. That is not renewables that's making that change. That is simply a fuel switching. And then you're like, okay, well, 2020 looks great. We're on the great track. There was a small thing that happened in 2020, COVID. So no one traveled. So transportation went way down. Industry was shut down. So, you know, I don't want to paint a bad picture, but I think I should have almost cut it off at 2019 or 2018 to give us a trend of where we are in 2022. So understanding where we are, what the impacts are, where it's coming from, what are the targets? What are we doing from a policy standpoint? I hope these are right. I pulled them off some websites yesterday. Again, the Pacific Northwest isn't my strong point. I'm getting better at it. Across Washington, Oregon, California, and the west coast of Canada, so the whole western seaboard, you see these very aggressive targets. You know, 95% reduction by 2050, net zero by 2050. There's sort of this recurring theme that policymakers really want us to push hard on reducing our emissions and get towards that net zero thing so we can start to mitigate the worst impacts of climate change. That's sort of our policy directive we begin with. And here I'm just trying to paint the picture of why are we doing this? So how do we mitigate this impact? There's a lot of people who've been focused on this. The most plausible way to reduce global CO2 emissions is to increase the role of very low carbon technologies in electricity generation, and then use that electricity in transportation and heating. So fundamentally, they've gone back to this target. They've said, let's go make electricity carbon neutral, and then let's use electricity to take over transportation and industry and make those carbon neutral. So they've taken those sort of top three, which is 75% of our emissions, and say, if we make lots of renewable electricity, we can take those on. So just to sort of simplify, step one, make a lot of renewable electricity. Step two, use it to substitute for fossil fuels, primarily in transportation and heating. So as we look out, and there's thousands of these studies looking at what's the transition going to look like? What technologies can we rely on? So this is by DNVGL, which is a global consulting company, looking at between 1980 out to, I think this data actually ended in 2018, where we've globally produced our energy, electricity, and where we're going to go. The red line sort of gives you a perspective of where we are now. So I think the big thing from this plot right now is we're probably looking at 100% increase in the amount of electricity we need to produce between where we are right now, which we've done since mankind existed, and where we need to be by 2050. So hopefully that gives you a scale of the build-out challenge if we really want to mitigate the worst impacts of climate change. The other thing I want you to look at or notice is when they look at those new technologies, there are three. Well, there are a couple more, but really there are three. There's offshore wind, onshore wind, and solar. And that's not because other technologies don't exist. It's because they don't, in these modeling studies, they're like, I need to know the cost. I need to know the cost projection decrease over the next 50 years. I need to know the density that I can deploy them at. I need a robust data set, which don't exist for emerging technologies. So when you see this, the reason why solar and wind dominate is purely because they don't have enough data on everything else to drive these models. But there's also some other nuances in here. So, solar and wind. There's a lot of people that saying, let's do solar and wind, and then we'll electrify. So we'll do solar, wind, and EVs, and we'll get to net zero by 2050. The scale of that between now and 2030 on the left-hand side, that's capacity addition. So 2010, we're at what, 220-ish? And we need to get to 1,000 in the next 8 years. 5 times increase. Seems tough. Also look at the amount of electric cars that need to be sold. So when people show you these plots like I just showed, it's important to sort of dig down into the data behind them and start to be like, well, what's feasible here? The other thing is if you rely on solar, there's a difference between cost and value. So what I've got here is a plot of the electricity prices in California. So the price is the purple line. So you see it starts, and it's on the right-hand side, the right-hand axis. So you see it sort of starts at around $30. It goes along, you get your midday peak, your morning peak at like 6 a.m. It goes up to like $33. By noon, it's negative $10. So at noon, California is paying Oregon, Washington, and British Columbia to turn off their hydro reservoirs, and they're paying us to use their electricity. And then it goes back up. And that's purely driven by the opposite slope, which is the green line at the bottom, which is renewables. In California, that's really just solar. So solar comes on at 8 a.m. and turns off at around 4. And it drives this change in the electricity price. So while solar might be incredibly cheap, which is what the story you hear in the news all day, at the scale of deployment they have, it absolutely has zero value. It's actually expensive. It costs them money to put more solar. For it's every negative $10, you're paying someone to take that. So there are drawbacks. It's not like this panacea, just put more solar out. What about wind? Wind's great too, but remember that scale question of how much we had to build out. Wind takes up a lot of space. The top left there is the scale for the same amount of energy, how much land space do you need? So natural gas, 0.1, nuclear, 0.3, coal, 0.8. This includes extraction and transportation and processing. Solar's 14, wind's 37. Now, this includes the area in the farm and the assumption that you can't use that space, which is wrong. You can use the space under wind turbines, but it just gives you a scale of what needs to be done. So on the on the lower left is where we sit with regards to land use for electricity production right now. On the right is where we need to get to by 2050. So we need a lot of land. Last time I checked, land wasn't going for free and people weren't sort of, yeah, you can take my farm space, that'd be awesome. We need a lot. You know, the numbers are wrong, but I think the message is we need a lot of land to start to do this. So a couple things, you see that offshore wind piece, which I'm sure is a topical discussion here. The other thing I want to say is this doesn't get us to net zero. This doesn't get us to any of our policy goals because there's still gas-fired, oil-fired, coal-fired at the bottom. And that's where I see an opportunity for new technology. In my specific case, I'm pretty bullish on wave energy and offshore wind energy. The other thing that I think is interesting is we look at the role of new technology, and I've sort of hinted at this. By 2030, these are sort of where they see those changes coming from. So 2030, behavioral change can get us 4%. Technologies that we can buy right now gets us from 4 to 84. And then the last 16 is from new technologies under development. By 2050, that whole situation's changed. About 50% of the necessary technologies for us to get to zero or get close to zero are still things under development. They are still the emerging renewables. They are still things that are in the lab, so to speak. So hopefully that gives a context of why I think looking to the ocean, looking to marine renewables is an important thing. This is a map of the technical power potential of the US marine renewable energy resources put together by NREL. It just sort of maps, so wave energy, which is our sort of blue, our darker blue, tidal, the orange, ocean current resources, which is the lighter blue, ocean thermal resources, so differences in temperature, and riverine current. So these are all the technological spaces under the Water Power Technologies Office at the Department of Energy. So this is their sort of mandate. And one of the things you notice is on the West Coast, you know, Alaska's got a huge one. Alaska does have a huge theoretical resource. It also tends to get iced up every winter. Hawaii's got a massive resource, but can they, like, you can't develop that and then try and get it back to the mainland with a really long electrical grid. The West Coast has a very, very active wave climate, that 250 in the terawatt hours a year. One of the other benefits when we start to look at it both, so we got a good resource. Two, I've got that same plot on the left of the just for context, when renewables come on, the price. On the right-hand side, I've got a plot of just a very quick one of the electrical demand over a couple of year period in Oregon and the availability of our wave energy resources. And the most important thing to have value in the market and mitigate just building thousands of things that we don't use is that the demand must meet the generation. So our demand for electricity, when we turn on our toasters and our washing machines and everything else, if someone else needs to be making it at that instant too, it's not, energy, electricity isn't this thing where you can put it on a shelf. Yes, we're getting better at batteries and hydrogen and things, and those are important. But the status quo is we need to make it at the exact same time someone demands it. So electricity generation that's get made at the exact same time what people ask for it are incredibly valuable. And that's one of this great complementarity between wave energy and our electric demand in the Northwest. Another thing is we need diversity. We can't rely on a single technology because they all generate at the exact same time. So, oh, that didn't work. So here we have solar, a map of solar in California and wind in the BPA region, which is Bonneville Power Administration's region. And solar, you know when the sun's going to come up, you know when the sun's going to go down, you know when you're going to get solar power. So that's great. It's easier to plan around. But if you looked at that curve for the wind in the BPA region, and you're responsible for making sure that the power and the power's on every minute of every day, that's not a nice picture. Like that doesn't give you a lot of confidence in your ability to manage that and buffer that and integrate it. And as you have more and more and more of it, so it dominates the electrical grid, that challenge gets harder. And then on the far right, we've got the gross wave resource. So I just pulled this off Surfline just to show that one of the benefits of wave energy, it's a fairly persistent resource. So our waves sort of, a storm and the resulting swell will sort of come up and go down over a period of 2 to 4 to 5 days, depending on where it's coming from. And we can predict it really well out 6 or 8 days, which isn't something we can do with wind. So just going back to my point, predictability is incredibly valuable. So what are wave energy devices? I'm sort of going to get us back towards what do I do? So there are a number of different technologies to figure out how do we harness the power in waves. Some technologies sort of pivot at a single point where they're taking advantage of the water elevation profile. That's on the far left, far right. Some are like a flap. So as the wave passes, they push a flap back and forth. Some just against the reference frame of the seafloor, they just move up and down, and that pumps. Some are like a rotating pendulum, like a self-winding watch, where you can put everything in a sealed container, you put your generator, everything, and there's no interaction between the corrosive ocean environment and your technology. So there's a whole host of different ways to generate power. Some of them are pretty big. So this is one built by Vigor Shipyards up in Portland. It's just to give you a scale of this device. I think you can see the scale. I actually don't know what the dimensions were. But this device was built, it's in Hawaii right now being tested. But these devices are getting built. It's not just purely in the lab. They are getting built at scale and they are moving. So why Oregon? I sort of gave a context of why we need to do this, what sort of wave has to offer, but why here? Why does OSU put so much time and effort into this? And I think there are a number of reasons. One, this is a map developed by the National Renewable Energy Lab of resources in the contiguous US. And the units are in kilowatts per meter. So this is a meter of wave crest, like just that from the seafloor up to the water surface. That's how you measure wave energy. It's like the flux of energy through that meter width. And you can see the Northwest is where it dominates. It's Washington, Oregon, a little bit in Northern California, but that's where the best resource is. Additionally, and I'm really intrigued to see how this shows up, this is a map of the transmission infrastructure up and down the West Coast. So this is the electrical transmission. These are all our transmission lines that go from hydro dams in British Columbia, Washington, and Oregon down to the demand centers in California. And it shows solar farms from Nevada shipping power over. But one of the things that you may or may not be able to tell, I'm not going to get outside my box, but there's not much transmission capability on the Washington coast, and there's not much on the California coast. Oregon's one of the few people that has a robust transmission infrastructure along the coast. So when you're going to build a new sort of suite of generation technologies, you can plug it right into the grid in Oregon. In California now, you have to go and build a transmission line, and transmission lines have impact. Everything we do has impact, but building large-scale transmission lines have impacts. And that's natural impacts, economic impacts, social impacts. So if you have infrastructure you can leverage, you should probably do that. So those are a couple of reasons of why Oregon. The other reason, 100% biased. It's because we're here. So the Pacific Marine Energy Center it's sort of a collaboration of the willing between Oregon State University, University of Washington, and University of Alaska Fairbanks. And our vision is to connect people to the power of the ocean. And we think that by responsibly advancing marine energy through expanding scientific understanding, we are academic institutions, engaging our stakeholders, and educating student workforce, we can start to have a responsible discussion about how, when, what, where, who. Across the center, we've probably got between 100 and 120 graduate students, faculty members, and staff members focused on this. So it's a deep pool. I often joke that we're not a mile wide and an inch deep. We're a mile wide and a mile deep because we have experts in every single one of these spaces. If we need to know about sediment transference or EMF or existing ocean users or forecasting wave conditions, we can go and tap someone on the shoulder who's done this for their career and said, how does this apply? How do I take your piece of work and intersect it with this marine energy research as we move forward? So it's a good reason why we're sort of internationally renowned as an academic leader in this space. The other thing we have is incredible facilities. and I don't even have this building on here, but we have some of the best facilities in the country, if not the world. So a developer, a technology person can come with an idea on the back of on an envelope or a napkin, and we can help them numerically model it. Then we can take it into the lab and we can test it at Hinsdale, the OH Hinsdale Wave Research Lab, which is the biggest non-military wave tank in the country. And we can start to understand hydrodynamics. If it's an electrical power takeoff system, we can take it into the Wallace Energy Systems and Renewables facility, the third one across, to test how do we integrate it. We can bring it, if it's environmental, we can bring it out here. Now I know Drummond has lots of other things, so I shouldn't just put environmental there, but that's Dr. Sarah Henkel, who leads a lot of our work for us to understand what is in some of the environmental monitoring. And then finally, moving forward, we're going to have PacWave. PacWave is the first pre-permitted, grid-connected, fully energetic open ocean test facility outside of Europe. So PacWave actually has two sites, the north site, which is on the left, and the south site, which is on the right. Just for the essence of time, I'm just going to talk about the south site. This is this grid-connected test facility. PacWave's been in development for about 12 years now. It took us 10 years to permit it. It's 4 square nautical miles off about 7 nautical miles offshore from Newport. It took 10 years to permit because we went to the regulators and the permitting agencies and said, we would like a permit for something that doesn't exist yet. You can imagine how that goes over. We're like, we need a permit to test devices that we haven't come up with, because we need to be able to get them in, deploy them, test them in a safe environment, and be able to get them out quickly if something goes wrong. So it took 10 years. But we're sort of on the right track. These dates, I would shift all these dates by probably a year. So we did all the directional drilling this summer. On the far right is where we'll build the utility connection and monitoring facility, where we do all our grid ties. That'll hopefully be done by the end of next summer. In 23, 24, we hope to pull the cables from Driftwood State Park out to the PacWave site. And then in 23, 24 is when we hope to deploy our first technologies at the site. And this is a big deal. There's been nowhere, you could go out to Hawaii and go through the permitting process, or you went to Europe to test your device. So back in January, DOE announced the first tranche of funding, around $24 million, for the first set of companies to come test the devices, so at PacWave. So not only we're building the test facility, but DOE is partnering heavily with us to make sure there's a pipeline of companies to come test it. And it's not just the generation companies, but there's also a lot on how do we understand the environmental monitoring, the instrumentation systems to do this in a responsible manner. The highlighted ones that just come, well, those are actual technology deployments. We've worked within PMEC, the Pacific Marine Energy Center, we've worked with every single one of these companies. On the far right is a Nacilla power device that's currently in Hawaii getting deployed. It's called their Triton C, or their Triton community scale device. But this is just to get an idea that there's a full pipeline of companies coming to PacWave in the next number of years. So how do people on the coast, how do our coastal stakeholders feel about some of this? So this was some work done by Hilary Boudet at OSU a couple years ago now. We got some work to follow up here, trying to understand, of all the renewables technologies, or all the energy generation technologies, how do people feel about this? And this is California, Oregon, Washington, and British Columbia. And so WAVE was in there, and 4% of people think we should reduce the amount of WAVE. We don't have any WAVE, so it's pretty hard to reduce it, and it's great. People generally like things they've never seen before, but that whole great promise. So take it with a grain of salt. But there is a huge amount of interest in seeing this move forward. Additionally, on the far right, across the political spectrum, there seems to be the broader support to seeing this as a sector to move forward. And whether it's because we can make an argument about US domestic manufacturing and US leadership in a space and not being technology takers, but technology developers, or whether it's a climate change imperative, there's a great story around marine energy that we can use. So a couple examples of projects on the go. I'm still doing well for time. So this is a project that we've just got in the Wave Lab right now, in the Hinsdale Wave Lab. This is an open source wave energy converter. So if I use the acronym WEC, Wave Energy Converter, So one of our roles that I think one of the most empowering things or the greatest things about being in the academy is our ability to support a much broader sector than a specific company. And so we applied to DOE, Department of Energy, to say we want to build a wave energy converter that is 100% open source. We're not going to hide anything. So if you want to know how much it cost, what our bill of materials was, all the disasters we did in the building and the design, anything of that, it's all going to be open source. And it's for the community. You're like, well, okay. One of the biggest things about this is there's so much investment in supporting individual companies. And if those companies progress and become commercial, that's great. But if they fail, we lose a lot of knowledge. And that slows progress for all of us. And again, in that climate change imperative, we don't have time to lose knowledge. So the goal here was to create something that's open source so anyone can use it. So we can take these techniques that have been used for industry to help them accelerate, do them on something open source and tell everybody about it. Additionally, there's a workforce challenge in getting into the marine energy sector. It's a hard problem. It has the intersection of engineering, oceanography, social science, environmental, everything sort of comes in. So we're trying to figure out, well, how do we reduce that barrier to entry? So one of the things about this device is it's modular, so we can test individual components of it. So on the far left, we've got a person to scale, so it's about 12 feet tall, weighs about 900 pounds. And how it works is that gold bucket will follow the water surface, while the green spar and the heave plate at the bottom stay fairly stationary. So as the gold bucket follows the water surface and moves up and down, you have this relative motion between the two. And that's the goal. So it just was deployed yesterday in the wave tank for the first time. But the goal is, again, open source everything. We're going to tell you everything about this technology to hopefully help people accelerate their progress. And after putting these together, I feel kind of bad because they're all sort of engineering specific projects. But the other one we're doing is we're trying to understand offshore wind a little bit better. As we move towards floating offshore wind, which we need to do as we move forward and trying to hit these targets that we have, we need to make devices that float. And one of the challenges is you can't, like this, the Lupa, the last one, the lab, you can scale it down by 20%. So by sort of dimensions, you can make it 20 times smaller. You make your waves 20 times smaller, and you can do a really robust experiment that helps you. The problem is scaling water and scaling air properties are different. One's Froude scale, one's Reynolds scale. So when you see cool experiments on BBC of a little wind turbine floating and bobbing and blowing air past it, it's wrong. It's just fundamentally wrong. It's cool, 100%. I am a sucker for doing cool things, but the physics are wrong. So what we decided to do with this experiment, this is a Department of Energy wind office project, is we said, well, we got a great wave tank. Let's build the floating platform. Let's put that in the wave tank because then we can capture all the viscous effects, all the complexity there. But because we can't scale the wind, we'll run a numerical model of the wind, and we'll take the forces from the numerical model, and we'll use a robotic arm to manipulate it. So we're doing a real-time wind simulation through the robotic arm coupled to the dynamics of the floating wind platform. It's hard. We'll see where we get to. But if we can successfully do it, the goal is here that we can test lots of different platforms really quickly at, this is about a 50th scale of a full-scale device, for like 10 grand. You can come make one. We can test it for you, as opposed to spending $50 million to try and build a full-scale one and put it out in the ocean. We can rapidly prototype in the lab. What do we do with the power? That's another question. Like, is this power valuable? Going back to the solar question. So there, again, we don't have a full-scale wave energy converter. So what we do is we run numerical simulations. So we've got buoys out at the PacWave site. We take those wave conditions, we put them into a numerical model with whichever wave energy converter we like, and then we actually run it through an electrical grid emulation through the Wallace Energy Systems and Renewables facility, where we run a motor generator pair. generate the amount of power that that wave energy would convert, and then we actually stick it into the campus grid, the OSU campus, my apologies, the Corvallis grid. So we can start to understand how does that affect power quality? How does it change flicker? How does it have impact on some of those electrical questions? So that's a neat one. We're starting to, again, we're trying to do all the bits around the edge so that the companies can focus on the IP. You know, and people are like, well, that's pretty small. What are you just powering Corvallis grid? There are a lot of remote communities that are on a very similar scale. And a lot of these remote communities, so we've got a Canadian map on the left and an Alaska map on the right. All the red dots are diesel. So all of those remote communities are powered by diesel. The green dots in the Canadian are biomass. And then there's some blue ones, which are hydro. Gray are natural gas, I think. So there are a lot of disadvantaged, energy impoverished communities who are relying on diesel and the associated price volatility to try and run their communities. On the other side, there's Alaska. And if I get this right, I'm always confused by this one. I think blue is diesel. Yeah, blue is no renewable energy, which I always thought, how come no renewable is blue and renewable is red? I feel like someone's playing a game with me there. But it gives you the scale of, there's a huge number of these remote communities relying on a diesel generation to sort of run their communities. And I think we have a sort of social imperative to try and figure out another way to do this. So a lot of my discussion thus far is focused on large scale, big. But the solar industry didn't go from the laboratory to like solar farms of acres. They made the calculator. Like that was their first step. They're like, we're going to power a calculator. So there's been a lot of effort recently to be like, well, what is the wave energy's calculator? What is our calculator? So the Department of Energy's got a huge effort called the Powering the Blue Economy. We're just saying, what can we do at smaller scale? So can we power ocean observing buoys? Can we power underwater vehicles? Can we do marine algae? What about desal? So the Department of Energy has really pushed their vision or their aperture of what renewable energy can be, and where do we start? So the Ocean Observing Prize was one of those. So how do we use marine energy to power ocean observing? How do we use it to make water? OSU actually had a team in the Marine Energy Collegiate Competition, which is a DOE competition, and they developed a wave energy converter to make desalinated water post-disaster response. They came second in the country. They did a really great job. Another effort with some of our robotics colleagues is saying, well, let's try and power underwater vehicles. And from a number of reasons, this makes sense. One, if we need to run an underwater vehicle, we have to generally take a large ship out to sea, which costs a lot of money, huge amount of investment, and you only can be there when the ship's there. So can we create sort of what the robotics folks like to call resident autonomy, where they can be there all the time and understand things? And that, you know, the military probably wants to do military things, but from like a NOAA science perspective, it's like, how are things changing on that site? Can we have constant measurements? If I could produce you all the power in the world, what different sensor would you place? Because right now, most of our science experiments are like, here's our energy budget. Who wants to divide it up? You get some, but none of us get enough. But if we can produce as much power as you want, what would you change? So this is one where we're doing underwater vehicles. This is a test where we're starting to oscillate so that that system on the right is a dock, and we're moving it as though it's connected to a wave energy converter, and that ROV is completely autonomous. So right now it's purely being driven by AI and some, they look like, what are those things you scan with your phone with all the black and white pixels? Yeah, and it knows where to go, and it autonomously went and docked in as we moved it. So this is just the beginning. We're looking at different types of wave energy converters, trying to understand when we start to put farms of wave energy converters or wind turbines or whatever offshore infrastructure, can we have ROVs on site permanently that are powered by the generation, but then can also do O&M for us? They can go and look at things, they can understand it. So in the middle of winter, when it's, 48 feet out at sea and no boats going out, can we still make sure these pieces of equipment are safe? So the other cool thing is, a lot of the examples thus far have been sort of, here we built something nifty and shiny that people like to take pictures of. But the other thing we try and do is a lot of sort of open, I'm not going to say open source because we do use some commercial software, but developing frameworks so we can start to understand all the coupled aspects of this. So here we're looking at underwater vehicles and a wave energy converter. So on the far left, this big block is, here we're trying to understand all the hydrodynamics. This is numerically of a wave energy converter tied to an underwater vehicle, tied to a dock. And in real time, it's sort of 100 hertz. Can we understand exactly where all this thing is going to move? And then can we tie it at the same time to sort of an AI-driven navigational autonomy algorithm so that the ROV knows where the WEC is and it can sort of mate them and understand what are the thrust requirements? What do we need to build from an engineering perspective to make that happen? And at the same time, can we track how the power is so we can sort of look real time at what the conditions are offshore? This is what a wave energy can produce. We could probably do this sort of duty cycle on the AUV. It could probably run this long so we know what battery sizes to put in this. And we can couple this all in real time through this simulation. So over on the far right, it's just a visual. That's that wave energy converter, that open source one at 20 times scale. There's a little dock and you can see the little, maybe you can see the little red dot. That's an AUV. So we're trying to develop the numerical framework to start to understand these things. Really with the goal of, we need to understand the numerics, we need to understand the physics, we need to understand the social side, we need to understand the environmental side, all to drive us towards this new future. So coming back to the past cannot represent our future, the future. I think a lot of people often look at that and say, well, here's the challenge. And I guess I look at that and I'm like, I see opportunity there. I see in the academy and what we do, and as a student or a postdoc or a faculty or a staff member, that's our sort of mandate, is to look far down the line and figure out what do we need to do and how do we do this in the right way. And that sort of gets me pretty excited. So I see this as an opportunity. I see Oregon being a great place to do it. I see OSU being a fantastic place to do it. So that's me. I'm looking forward to taking some questions.
All right. Thank you so very much. So this is our chance. Let's ask some questions. I'm going to start and see if there's any questions online at the moment. Okay, so for folks online, go ahead and put your questions into the chat and we will take time to answer those. For folks in the room, anybody have a question to kick us off? All right, Drummond, I'll bring you a mic.
Thanks, Bryson. That was a good sense of why I want to go and hang out in the waves more and why we're lucky to be where we are. I'm curious as to, I guess I would say kind of the student engagement between PMEC and PacWave, and when companies start coming in there, is the intention that there will be some kind of workforce training, student training engaged there, or what does that kind of look like?
So the best way to think about that is PacWave team might disagree with me, so don't tell. I see PacWave as an incredible piece of infrastructure. It is a ship, or it is a wave maker. It is an incredible piece of infrastructure. What PMEC's role is trying to understand how do we leverage all these incredible pieces of infrastructure to do great research, to move the needle as we move further. So PacWave's not, they'll have some interns and things, but that's not fundamentally their role. Their fundamentally role is to provide a testing service for people. At PMEC side, our role is to make sure we engage people at all levels. And that could be, most of our work's graduate students, but we started a marine renewable energy club on campus to start to integrate with undergraduate students a lot more. The marine energy collegiate competition went out to a lot of the schools and they built little wave energy converters where they could move them and students could build their own. So hopefully we'll start to build that in, particularly as PacWave comes online and people can go to the coast, go down to Driftwood and sort of see what's happening. So that's definitely a big part of it. And I think now that we've sort of got over some of the hurdles of PacWave, we can start to be like, okay, now where does the workforce come in?
All right, question online. Go ahead.
Okay, we have a question. Do you currently have an idea of how much the energy generation methods will affect marine ecosystems and organisms?
So I guess whenever I get sort of a similar question there, I always sort of like to put the perspective on everything we do has an impact. Like absolute, and there's nothing we could do. There's no silver bullet. There's no just solution that's going to fall out of the sky that has no impact that are going to allow us to mitigate the worst impacts of climate change. So what are the impacts of marine energy going to be? We don't know. We've done a lot of really good science on small scale things, on anchors, on moorings, on smaller scale things. And that knowledge is very internationally internationally shared. And my interpretation is that it looks pretty good. But we aren't really going to know until we deploy, until we actually put devices in. So PacWave has a 24/7 monitoring requirement on all our environmental parameters, and that'll only get increased as we deploy devices. And the goal is, if you deploy a device, you've got to have a plan to get out of there if we see something adverse happening. But until we actually start to deploy them, we just don't know.
All right, question in the room. Hang on.
Really enjoying your presentation here today. Thank you. Early on, you spoke about the importance of predictability and for energy generation, with wave energy being much superior to wind energy, but more predictable than waves are the tides.
Correct.
And I remember early on quite a lot of interest surrounding energy, tidally driven energy generation, but I didn't see anything appearing here. Maybe it was there and I missed it. Could you talk a little bit about where the momentum and interest has gone?
Yeah, no, for sure. That's a great question. And you're 100% right. The predictability of tides is far superior to waves. The challenge with tides is, you need a decent velocity of water to actually generate useful power to overcome friction and a lot of things. And generally that requires a constriction. So it requires a large water body to flow through a constriction to get the speed up high enough. And the orange dots are our tidal resources in the US. And they just aren't that big in the US context. And they're very much like in Puget Sound and San Juans, and they're huge environmental and sort of concerns there, very grounded ones. So while there's a lot of research going into it, it's still moving forward. It just doesn't have as much emphasis as maybe it does in the UK, where their tidal resource is just so much larger than it is in the US context. There's a lot of work going on in Cook Inlet in Alaska, that sort of furthest left orange dot. And then there's a bunch of work up in the Northeast on tidal. But in Oregon, we just don't have a tidal resource of any sort of scale. And I think across the country, there's a lot of work happening in there, but it's also not as ubiquitous. So if you're going to try and do these powering the blue economy, these smaller scale things, you're sort of locationally limited. It's not going to be a solution for everyone. But in terms of progression in Europe, yeah, they're getting pretty close to full commercial projects where they could deploy, make money without relying on the public purse to make it happen. So in Europe, yeah, they're far ahead in that space.
All right, question online.
Yes, we have been hearing for years about OSU's wave energy research, yet it seems that almost overnight there was call areas for wind energy areas and a big push from BOEM for offshore wind.
Yep.
Why is that?
So yes, OSU, we've been focused on wave energy for a long time. It's a hard challenge. And I think, often we get pushback like, why is this taking so long? Doing anything in the ocean, I'm sure most people here know, is hard and expensive. It's not like you could jump in your pickup and drive to the bottom of a wind turbine and take the elevator up and fiddle with a couple things or put another solar panel out. You need a vessel, you need the weather to be nice, you're also putting in an incredibly corrosive environment, which generally, like the ocean, likes to corrode and eat and break things. So it's just a harder environment to work in. And as a result, it's more expensive. So you got to do a lot more fundraising. You got to work with your agency a lot more to try to get the scale of funding to push it forward. So it's just slower. Around the offshore wind sector versus marine energy, the offshore wind sector has really benefited from the terrestrial wind sector. And we've been making energy from the wind since sort of the beginning of humans making power and moving things. You know, windmills have been around for as long as we can sort of look back on our energy utilization. So they managed to do a lot of work on land to sort of accelerate that technology. And now to put it into floating offshore wind, which BOEM's working on, is they're sort of taking a lot of stuff they've learned on land and putting it on a floating platform. So that's why, again, a lot of our efforts recently have been focused on that floating platform and what do the dynamics of that floating platform look like? And why is it showing up in BOEM's radar? It's getting towards cost competitive. It's getting pretty close to being cost parity. That being said, it's probably a decade before we see one of these systems out. That's how long it's going to take to do this. So, you know, if companies are going to bid when these areas come up in Oregon, they're going to be doing with a decade-long time frame. So hopefully that answers some of the questions.
All right, anybody in the room? Okay, go ahead, Don. Oh yeah, turn it on, just slide it up.
On now?
Yep.
Thanks for a great presentation. That's all really interesting. I am curious if you could maybe speak to kind of comparing so with floating offshore wind,
yep.
there's a footprint associated with, you know, having these platforms cabled and
yep.
and obviously, as you alluded to, the wave energy technology, there are a lot of different potential technological routes that are
yep.
in development. I'm wondering if you could give kind of a sense of the comparison of the footprint of these different, or the spatial area that you need. Do you need like less wave energy devices to kind of equate to a very large wind energy generation site?
I'm trying to think how I can start to get towards that. Firstly, wind is sort of like an additional dimension. So it doesn't just have X and Y footprint, it's got like the height dimension as well. So it's got the Z dimension. So one of the benefits of going offshore wind is they can build turbines a lot bigger than they can on land. Because the constraint on land is you just can't transport them. You can't put them on the highway and drive them around corners because the corners are too tight. They can't go under bridges. So by going offshore, where you load things from a port or production facility onto a boat, you sort of get around a lot of that. So they can build them really big. They are going to be big. They're talking about 20 megawatt systems, which is like big as skyscrapers. They're not small. You don't do offshore wind 1 or 2. So they're at that stage where they've taken like hundreds of years of investment, not hundreds, but a lot of years of investment to organize technology. Now they're putting on a floating platform. The footprint, once you put anchor lines and moorings, it's going to be there. I think it's still an open question of, you know, will that area be an isolated area, or will you be able to co-use that area? And I think there's a lot of a priori sort of philosophies on that in the media right now. That it's like exclusionary, you can't come in here. I don't think that's real. I think we don't know yet. It could be that it could be a great co-use area. So that's an offshore wind. On the wave side, you know, we're not trying to build 20 megawatt systems. We're trying to build 1 megawatt systems. So it's going to be a lot smaller. And what does our technology trajectory look like is a little less clear than wind, where they're much further along that technology development. But all the deployments thus far have all followed a very similar trajectory in terms of what solar did and what wind did, that we all seem to be on the same sort of curve of performance versus cost. So I didn't really get to your geographic scale question, but hopefully something there. Yeah.
All right, I think question online. Go ahead.
Yes. Are there any known drawbacks to wave energy in terms of negative impacts on wildlife? For example, are there any potential entanglement issues for marine mammals or issues associated with electrical transmission lines that may affect organisms that depend on electrosensory organs, such as sharks?
Okay, so on that one, I'm going to go back to this slide where I get to talk about all the other experts and not myself. So there are much better people in the room to talk about EMF and what that impact would be. But we do have a study right now with Sea Grant looking at that exact question. So on the electrical magnetic fields, I'll defer to other folks who know more. To the previous question around entanglement risk, from all the, in order to keep these devices on location, you need to have the cables fairly taut. They like taut in the greatest sense. You're not going to have loops. If you start to have sort of free floating loops, you're going to create a giant mess for yourself, and it's going to sink your boat. It'll just slowly draw you down. So they are fairly like static lines. Can entanglement happen? Maybe. But I feel like the real issue, I don't know. My personal opinion is I don't think that's a real issue, but again, until we deploy them, we don't know. So I think I default back to that question. We need to deploy devices with a very robust extraction plan if things, if there are impacts.
All right, I'm going to hand this off to Kyle. He's going to answer the question.
Okay, there we go.
I'm not going to answer all your EMF questions yet. Actually, back to the deployment. Well, two things actually. Do you know if there's planned to be a test facility for floating offshore wind, kind of like PackWave, but a floating wind?
Okay.
Because that would be really, I would love to to work with that.
Yeah.
But secondly, when you have the wave energy converters, like how deep is like how far offshore? What's the sort of the water depth? I assume it's going to be relatively close to shore as opposed to offshore wind, which they're trying to push it way off, you know, almost off the shelf, or at least at the edge of the shelf.
So to the first question on sort of a test facility for offshore wind, no, there isn't one. You know, the University of Maine is deploying a turbine, a floating offshore wind turbine. But it's also a very different sector. You know, they're no longer at that. We want to understand how our technologies and do some deployments. They're at the scale now where they're commercial. The math pencils out. It's economic to go to scale, which wave energy is. So, you know, I think where we do have significant opportunities with PackWave to answer questions, science questions that would benefit both the wave and the offshore wind is anchors, moorings, connectors, things that are consistent to both industries. But I don't, you know, my gut reaction is I don't think the offshore wind sector needs a test facility anymore. They were generating technologies. They've figured out their product, and now they're building projects. So that was the first one. The second question was, oh, depth. Like you're right. You're trying to put it as close as you can, because the most expensive part of your project is the cable. So the less cable you have to buy, the more cost effective it is, but you're putting it as far off shore that it doesn't get in breaking waves, which destroy it. So that's really the tension. You know, I would say most devices probably needs more than 60 meters of water, but they don't want to go out to 200, 300, 400 because the costs of doing so are just exorbitant. It makes completely cost ineffective. Yeah.
All right, so we're getting close to time, but we're going to take one more question online and one more question in the room. So go ahead, question online.
Okay, are fishers going to be displaced from fishing areas with wave energy? There's a concern that with offshore wind on floating platforms and it being dangerous, they might not be allowed to get close to the wind platforms to fish. Is there a similar danger with wave energy? Would the fishers be able to get close to wave energy platforms and fish around them, or would it be a closed area?
So I don't know if it'll be a closed area. It's still an active area of sort of development. You know, inherently, whenever you deploy something in the ocean, it's going to displace somebody. Like there's no free space as far as we've been able to ascertain. So you're definitely going to displace somewhere. The fishing community will have some impact. You know, how big is that? What does that look like? How do you create benefit where there are challenges? If you're sort of removing some area, how do you make sure there's equal benefit to the community so that detriment versus benefit balance is there? You know, but I still also I come back to the stage that I think there's a lot of discussions in the media right now about, well, this is a closed off space because we're doing this here. This is a closed off space because we're doing this here. And I don't think those have been determined. I think those are still active questions that we can research and we can understand. And in the university system, that is something we should look at. Like, are there co-benefits? Are there co-challenges? Are there opportunities to work together? What does this look like? Let's not make any broad statements until we've started to deploy and start to understand what this looks like. That's personal opinion.
All right, so questions in the room. Okay, I've got 2, but I'm going to go up to Lisa. Sorry, Jessica.
Hi, thanks for that great talk. Unless you had a plot of Oregon electricity demand against sort of wave energy transport, and unless I misunderstood what that wave energy transport line represents, to me it looks like production doesn't meet demand a whole lot throughout the year, unless the brown line doesn't actually represent production.
Please do not read this as a scientifically robust plot. This is 100% not. It is. The goal here was purely to show the coincidence of winter demand and generation potential. So month to month variability, 100%, is really just trying to show in the summertime we don't demand a lot of electricity in Oregon. That's changing with climate change and more air conditioners. Generally, what we want is power in the winter for heating. And that's when the waves are the most prevalent. So the goal was not to make a really robust chart. It was really just to show in winter we need electricity and there are waves, and in summer we don't need electricity and there are not many waves. That was purely the goal.
All right. If there are any other questions in the room, I think that you'll be able to ask them for a few minutes after our talk, but I know that our speaker does need to run away. For everybody online, thank you so very much for joining us. I hope to see you next week or to have you join us online next week. And one more time, let's thank our presenter. All right, everybody, till next time. Okay, folks online, we're going to end the presentation. See you next week.